Hello and welcome to DIY Machines. I'm Lewis and we're currently halfway through building our very own kinetic sand art table. Here's a quick reminder of what we'll have finished building by the end of this video. In the first part of this project, which you'll find linked to up here, we began by building the wooden table frame, installed the mechanics, and begun working on the electronics so that we were able to make our very first basic marks in the sand. In this video, we will be installing the smart LED lighting beneath our veneered wooden tabletop. We will also install a control panel onto the side of the table so that we can control both the LEDs and patterns without needing to use any other devices. And we will also install a Raspberry Pi, which will act as a 24/7 DJ for our list of geometric patterns to be drawn on the table. This video is sponsored by Thangs. Thangs is an online platform for designers, engineers, 3D CAD enthusiasts and more to come together where they can share, discover and collaborate on 3D models. They have over 2.4 million models in their database, and this number is growing rapidly every single day. And check this out, almost every model on Thangs is available to be previewed in AR using an iOS or Android device without any need to install an app. How cool is that? Their service makes it easy to collaborate together with teammates or upload new versions of your models. Thangs is free to use and offers unlimited uploads of your models. Go check them out at thangs.com. We'll kick the second part of our project off by building a simple frame to hold our LEDs in place. For this, you'll need to prepare 4 lengths of wood, 2 68cm long and 2 45cm long. They can then be assembled with the shorter length inside of the 2 longer lengths and held together with either screws or glue. Once you've got your frame into a rectangle shape, we can then make a small hole slightly larger than the width of your LED strip in one of the long sides of our frame. This hole wants to be about 2 centimeters inwards, and this is what we will use to pass the LEDs through shortly. We can then use 4 of our 3D printable LED corners to hold our frame into the center of our table surface. You'll find links to download all of the 3D models for this project in the description below. When fitting the corner pieces, ensure that the fabric our sand is sat on is pulled taut to help avoid any crinkles interfering with the ball's travels. As these 4 corner pieces which we just added to our tabletop also double up as handles, we can now remove the temporary screw which we were using to lift the tabletop in the first video. To prepare the LEDs, start from the end with a connector and the directional arrows pointing away. Run a length around the inside of the wooden frame and then trim it a little oversized, ensuring that you cut through the center of the pads as indicated. We can then thread them through the hole and then install them by removing the self-adhesive backing as you go, pushing them firmly up against the wood. To be able to easily connect and disconnect them later if we need to access the internals, we can use the plugs supplied with the LEDs. Prepare 3 60cm long lengths of wire and solder them to the red, green and white wires coming from the end of the female connector. We can also trim off the additional red and white wires from the male end of our LEDs. Join the 2 connectors to one another and then make a small notch at the edge of the 3mm board so that the LED wires can pass by. We can then thread the unconnected ends of the wires through the hole in our 18mm baseboard, which we made adjacent to where the control panel will be fitted later. Whilst here, we can also thread the USB and power leads for the CNC shield through this very same hole. Our control panel is next, and for this you're going to need another 3D printed part, the aptly named control panel. Now, this is the only part in this whole project that needs printing with supports enabled. I also changed out the filament for the last few layers of the print so that the text stands out from the rest of the panel. Begin by fitting the buttons and potentiometers to the control panel itself. We can then turn the control panel around and begin attaching the wires to the various legs. Now I'm going to be using some heat shrink tubing to protect the legs and wires from shorts or unnecessary strain once we've finished. If you'll be adding some for your project as well, then don't forget to add it before you've attached both ends of the wires to our buttons and knobs. Working from left to right with the potentiometers on our left, attach a 30 and a 6cm wire to the first leg, a 30cm long wire to the second, and a 6cm wire to the third. The fourth leg has the 6cm wire from the very first leg attached to it, and the fifth leg has a new 30cm long wire attached. The first button's leg has the 6cm long wire from the third leg attached along with a brand new 30cm wire, and the other leg on our first button gets a new 30cm wire. Each of the remaining unconnected legs have an individual 40cm long wire attached to them. Well, I got to the end of the control panel and realised I was trying so hard not to make a mistake that I completely missed connecting the sixth leg along. This is easy enough to remedy, and we'll add an additional wire now. Add a wire between the first button's leg, which already has two wires attached, and the unconnected sixth leg. Once your heat shrink is shrunk, the back of your control panel should look a lot like this. The last two buttons for playing and pausing the patterns in the sand will be attached to our CNC shield. Now I have gone ahead and added some DuPont style connectors to the ends of my wires so that I can easily slide them over the legs in the CNC shield. This is very easy to do yourself, and I have made a separate instructional video showing you how, which you'll find linked to in the corner and in the description below. Remove the lid on the CNC shield and optionally unscrew it from the table frame momentarily whilst we connect the wires from our control panel. Pass the wires through the opening for the control panel from the outside of the table. The wires coming from our pause button are connected to the legs labelled as hold, and the wires coming from our start button connect to the resume legs. The other bare wires coming from the control panel can then be fed through the hole in the baseboard. To create the mix of both 12V and 5V power levels which our project requires, we can start assembling our power system. For this, you'll need your mini 360 buck converter and the DC barrel which we assembled in the first video, along with your Wago style connectors. Trim the positive lead on our barrel connector to about 7cm long. The other we can leave at 12cm. Thread this connector through the 3D printed housing and secure it in place using its own nut. Attach a 3-way terminal to the positive wire and a 5-way terminal to the ground end. Solder 3 lengths of wire to the terminals on the mini 360 buck converter. A 13cm wire to the positive input and a 5cm wire to the negative input. Finally, a 6cm wire is connected to the positive output. The mini 360 buck converter is capable of outputting a range of voltages. We need it to output 5V for our project. So to set this, we'll connect it up to our barrel connector in our power supply housing, and then use a multimeter to set it to as close to 5V as we can. Attach the multimeter's positive probe to the positive output on the mini 360 and the negative probe to the negative output. You can set it to 20V output and then turn on your power supply. We can now use a screwdriver to turn the potentiometer on top of the buck converter until you get as close to 5 volts as you can. Once you're done, you can turn off the power supply, disconnect the multimeter, and we'll put the Mini 360 into our 3D printed housing. Once the converter is nested, you can add a 5-way terminal to its positive output. Now is a good time to fix this to the underside of our table frame. Make sure you remove the LED frame and 3mm baseboard with sand before you carefully place your table on its side with the control panel facing upwards. Use 3 wood screws to install it towards the top right of our base so that the barrel connector is on the right and the buck converter towards the top right. We can now take the power wires that come from our CNC shield and connect the positive to the 3-way terminal at the bottom, which supplies 12 volts, and the negative to one of the ground terminals. You can trim the length of the wires as we go if you find that any of them have too much excess. You can use some glue to tidy our Wago connectors away in a more tidier fashion. We will need more than the 5 ground connections that we have at the moment. To add some more, we can use a 5cm long wire to attach an additional 3-way Wago connector to the existing 5-way one. We can now connect the power connections for our LED lighting. The wire that you connected to the LED's red wire is our positive lead and should be connected to the 5-volt connections the buck converter provides. The wire you connected to the white lead is a ground connection and so can join the other ground wires in the wiring block. Next up, we will install the Arduino Nano so that we can put the LED lights and their control panel buttons through a test. We will upload the code to the Arduino Nano by first connecting it to your computer with a USB cable. Open the Arduino IDE and the code for our project. The code for the Nano is found inside the LED Arduino folder. Don't forget, links to download the code and everything else for this project are available in the description down below. Select the correct board type of Arduino Nano and the port for your device before pressing the upload button. We can connect the wires from our control panel's lighting section and from the LED's data pin to the Arduino Nano directly by soldering them to the board. Don't forget though that our Arduino Nano will reside on the underside of our table, so make sure all of your wires are threaded through the hole in the baseboard before you solder them to your Arduino Nano. But before we do that, I want to say thank you to everyone who helps enable me to make and share these projects for free online. First off is this lovely list of patrons who help support me with a small monthly donation. I'd also like to thank 3D Jake, who have supplied the filament for the prototyping and filming of this project. Thank you. If you would like to consider supporting this channel, then please take a look at patreon.com/DIY machines. Every little bit of help really does make a huge difference to the projects I get to turn out and share. The single wire coming from the pattern button is soldered to the pin D2 on the Arduino. The central leg of the brightness potentiometer is attached to A0 and the central leg of the speed control is attached to A2. 2 new 16cm long wires should be attached to an unused ground pin and 5-volt pin. The data wire coming from the LED's green wire should be connected to D6 on the Nano. The wire we connected to ground can be added to the power panel's ground connections, and the 5-volt wire to the 5-volt power blocks. This last wire is the 30cm long one that we attached to the first button along with 2 other shorter wires. This should be connected to an unused ground connection on the Arduino. When you reconnect your LEDs to the table and the 12-volt power supply, you should see the LEDs spring into life. You will also be able to control them using the button and 2 dials on the front of your control panel. The speed dial will affect the tempo of the animated sequences. Some of the patterns, such as the solid white one, are static, so they won't be affected by this control. The brightness dial will adjust the maximum brightness of the entire LED strip, and the pattern button will cycle through the inbuilt lighting sequences before looping back around when it gets to the end. Let's add our Raspberry Pi next. Now the Raspberry Pi is going to be responsible for feeding the G-code instructions for drawing out the patterns to our Arduino Uno line by line. For this, we're going to install a program called Octoprint onto our SD card. Now, Octoprint is primarily designed for powering 3D printers. In fact, I use it for mine here. For it to be more suitable for our sand table though, there are a couple of plugins which we can install and a few settings we can tweak. I'll explain how to do this now, but I also strongly encourage you to check the article for this project on my website, diymachines.co.uk, because here I'll list any revisions or improvements made to the software since filming this video. To flash the SD card for our Raspberry Pi, we can use the Raspberry Pi Foundation's very own Raspberry Pi Imager. Head over to the Raspberry Pi Foundation website and download the free Imager from their software section. Connect your micro SD card to your computer and open the Raspberry Pi Imager. Press Choose OS and then Other Specific Purpose OS. In this list, you should find Octopi. Continue on to select your SD card, and then we'll press the key combination of Ctrl, Shift and X to access the advanced menu. Check Set Hostname and set one. I chose mine as Sand Table. We will use this as a URL to access the table's web interface later instead of an IP address. You can then scroll down to configure your Wi-Fi credentials. Press Save and finally Write. It may take a little time to download the image, flash it to your card and then verify it, though it's a great opportunity to make a lovely cup of tea. When that is complete, we can remove the SD card and insert it into our Raspberry Pi. To fit the Raspberry Pi to the underside of our table, we need to print the computing case. The Pi is then secured on the standoffs with our 4 M2.5 bolts. The USB port should be facing the cutouts. This can then be secured with 4 wood screws with our 2 cutouts facing upwards. We can now connect the USB cable to our Raspberry Pi. Prepare 2 new wires, one 24 and the other 28 centimeters long. These will be connected to the 5V and ground pins on our Pi to power it. Now, as the Pi already has legs attached to it, I've gone ahead and added some DuPont style connectors to the ends of these wires. The longer 28cm wire should be connected to the 5V pin, which is the second pin up from the bottom left, and the adjacent wire goes above this so as to connect to the Pi's ground pin. The other ends of our wires are then connected to the respective power blocks. The long wire goes to the 5V blocks and the short wire to our collection of ground wires. The lid for our computing case can be printed next, and then once we've put the Arduino Nano into the second half of this case, we can fit the lid using 4 M3 bolts. The lid for our power panel will then follow this using the same M3 sized bolts. Reconnect the mains power supply and your LEDs should spring into life. Wait about 2 minutes for your Raspberry Pi to complete its initial boot before browsing to sandtable.local in your web browser. We will now be presented with the Octoprint Wizard. As mentioned earlier, this has been designed with the expectation that we will be using it to control a 3D printer, so some of the steps as we step through this wizard will be irrelevant for us. On our first screen, press Next. On the one asking if you want to restore a backup, press Next. And on Access Control, you should choose a username and password which you will be asked for when connecting to Octoprint in the future to control your table. Press Create an account and then Next. At Anonymous Usage Tracking, choose whether you want to disable or enable tracking and then press Next. At the Online Connectivity check, choose to enable it and press Next. At the Plugin Blacklist, choose Enable as well and Next again. For the default printer profile, for a name I entered Sandtable and model DIYM. Under Print Bed and Build Volume, uncheck Heated Bed, as we do not have one of these, and set the print volume to X as 525, Y 330, and Z 10mm. We can then press Next and finally Finish. The first plugin to install will give us better control of Gerbil. It is called Better Gerbil Support. To install it, click on the wrench icon in the top toolbar of Octoprint and then Plugin Manager from the menu on the left hand side. Click Get More and search for Better Gerbil Support. Click to install it and then restart Octoprint. It's as simple as that. There is one more setting though which we need to change for this plugin. Reopen Octoprint settings page, choose Better Gerbil Support from near the bottom of the left hand menu and then change the value of Hello Command to blank instead of the default $sign. After the Raspberry Pi has finished installing, we can add our second plugin. This is called Octoprint Playlist. This is what we're going to use to queue up a playlist of patterns and have our machine automatically move from one to another in a never-ending loop. This plugin does not reside on the official Octoprint plugin service, so we will need to download it from GitHub and upload it directly to Octoprint. Navigate to this web address, click Code, followed by Download Zip. To upload this into Octoprint, click on the wrench icon at the top again and reopen the plugin manager. At the bottom of the window, press the Browse button underneath the From an Uploaded File. Browse to the zip file you just downloaded from GitHub and upload it. Octoprint will automatically check it and then proceed with the install before requesting a restart, which you should agree to. Let's finish our work on the control panel next. Before we can fit this panel into place on our table, we need to finish checking that the buttons and dials are working as intended. We've already checked our section which controls the LEDs, so we just need to check the start and pause buttons. To be able to check this, we're going to have to set up our machine and get it drawing its very first complete pattern in the sand. For this, we're going to need an illustration which has already been converted into G-code. I have included a couple in the files you downloaded from GitHub earlier, so let's upload one of these to Octoprint now. Open Octoprint and then in the left hand column press Upload. Navigate to the drawing file called spiralingsquares.gcode and upload it. Before we can have the machine carve out the pattern, we need to connect to Gerbil and home the mechanism. Press Connect on the left. Now if this does not connect first time, you may need to try again. Once connected, you can choose Home in the Gerbil control window. Once the homing sequence is complete, and your sand surface and ball are fitted to the table, we can press Print next to our G-code file. Whilst the machine is drawing, we should also be able to press Pause and see the machine gently come to a halt, and then pressing Start should cause it to resume the drawing. Now we know that the control panel works, we can fit it into place. I use some glue to secure mine in place. Don't forget to check that your wires found on the inside of the table are still securely held out of the way of the mechanism. We are now very near the end of our project. All that's left to do now is to make the table frame and add some glass on top. Now I'm going to miter 4 pieces of wood together to make the frame and then finish mine with some real wood veneer. You could paint yours if you like to, or finish it in any other way you'd prefer. For the mitered panels, I prepared 2 lengths of wood at 683 by 170 millimeters and 2 lengths 883 by 170 millimeters. Both ends of each panel were then mitered at 45 degrees using my miter saw. I then used some pairs of pocket holes drilled into the ends of the longest panels to assemble them together. Once I was happy with the fit, I disassembled the panels so that I could veneer them individually. Now, I'm certainly no woodworking expert, and probably far from it, but I will show you what I did to apply the veneer to my panels. I chose to use some European oak veneer which I got from Oakdale Crafts here in the UK. I cut some lengths slightly longer than each of my panels and then applied some contact adhesive to the panel itself and also the rear of the veneer. Once this dried, after about 30 minutes, I brought them together carefully and used a small roller to apply pressure to ensure a good adhesion. A knife was then used to trim off the majority of the excess before using some sandpaper to carefully further refine the edges. I then applied some lengths of pre-glued iron-on edging tape to the inside edges of the panels using an iron on a very low heat. I then used sandpaper to tidy up the edges. At this point, I reassembled the frame so that I could apply the outside edging in the same fashion whilst ensuring that it met well on the external corners where it would be seen. After using a hoover and slightly damp cloth to remove the dust left from our sanding, I used some old rags to generously apply some boiled linseed oil to the edging and veneered surfaces. I left this for about 25 minutes to soak in and then removed the excess. 24 hours later, I repeated the process of liberally applying the boiled linseed oil before removing the excess 25 to 30 minutes later. Now, if you have used boiled linseed oil, you need to be careful of what you do with your rags, as they might spontaneously combust. Wash them through with some soapy warm water and then dispose of your rags in an outside bin. I then ordered some glass cut to size from a local supplier, which simply sits on top, allowing us to clearly see the art underneath, whilst it can be safely used as a coffee table. And that's the table completed. All that's left to do is for me to show you how you can create your own patterns using sandify.org and how to create a playlist to repeat one after another automatically. Head over to sandify.org. This is a fantastic community site created to help easily make patterns for your table. Before you start adjusting the various parameters though to create your own pattern, we need to change some details about the machine it will be drawn on. Open the machine tab and set the values for min-x to 5mm and max-x to 520, min-y to 5 and max-y to 325. You can then return to the draw window to create your own patterns. Adjust the various settings until you have created something you like and then press Export at the bottom of the window. Create a descriptive file name for your art and then in the Program Start Code box enter G1F2000. The file you downloaded can then be uploaded to your sand table in the same manner we did with the first drawing. You can also upload the eraser.gcode file which was included in your project's downloads. This is a simple pattern which zigzags back and forth across the entire drawing surface to help tidy it up occasionally. To create a playlist of patterns that will flow from one to the next automatically, open the playlist window and then press the Add to Playlist button next to each pattern you would like to add. You can queue up several like so. Check the repeat box and then press play. Whilst designing this project, I spent some time talking with Jacek from Moving Pieces Studio, who is also designing his very own high-end sand table. It is carefully casted in concrete, and their custom designed and engineered mechanism creates an absolute minimum of borders around the edge of the drawing area, which I think makes it look stunning. That's all from me in this video. I hope you've enjoyed watching it and might consider supporting my projects so I can keep creating and sharing these for free. You can find my Patreon page at patreon.com/DIY machines. Don't forget, on my website you'll also find FAQs, troubleshooting and instructions on how to build this in a larger or smaller size. Thank you for watching, have a wonderful day and ciao for now. Next, you'll need to make a small hole slightly larger than the width of the LEDs, about 2 cm inwards. I was trying so hard not to make a mistake that I completely forgot to connect